Good evening and welcome back to Vegas October 1 Sounds. You just heard a sound. What is it? That's the question. Because that essentially is what we have to do when we do acoustic gunshot analysis. We hear a sound. What is it? You have no clue where that sound came from. Most of you, though, probably recognize it as me snapping my fingers close to the mic. And we do that because inside our brain we have memories of, we watched some people do it, snap their fingers, and it produced a sound, or we recorded it in our brain and we can recall it and compare it. And that's essentially what happens in gunshot acoustics also. But remember, there's thousands of guns, thousands of calibers, thousands of different loads, thousands of millions of environments, and none of us has been exposed to all that to know. So we have to rely upon certain fundamental basics and physics to help us in our cause. In Vegas, we are fortunate, for we have thousands of samples of one type of gun. Actually, one type of gun is poor. We have thousands of samples of sounds which we believe to be gunshots. And we also have a small number of samples on a couple of other things that we believe also to be gunshot sounds. And then we've got bukus, an unlimited number of sounds that who knows what they are. Sometimes they sound like gunshots, sometimes they don't. But normally they work out not to be gunshot sounds, because a gunshot sound has a very specific frequency range. It has a duration, that is, the sound produced by the shock wave of a supersonic projectile. When it's created, it has a duration of less than 1 millisecond, and by the time that shock wave goes through the air and hits our recorder, and our recorder responds to it, oftentimes it gets contorted in ways which make it longer, less amplitude, change the frequency a little bit, but it's still fairly short and normally shows up in our recording devices as a signal that's approximately 1 millisecond long, maybe a little longer. The muzzle blasts, on the other hand, are longer. Similarly, when those exploding gases pop out of the end of the gun, and they create this, and they finish burning and exploding, and they create this massive explosion. That's a shock wave also, but that shock wave quickly dies off and turns into a normal sound, propagating outward in all directions, approximately like a sphere. And the duration of that, while it does spread over time in length, is about 3 milliseconds. Sometimes longer, sometimes a little shorter. But the two normally on most recordings are quite distinguishable in terms of duration and frequency. The frequency of the muzzle blast, of course, centers around or averages near the 300 to 600 hertz range, but it does have components that go higher and components that go lower. The supersonic crack is a higher frequency sound, and when it gets created, it goes up to 20 kilohertz and down to probably about 1 kilohertz. As it propagates through the air, being a higher frequency sound, it loses much of the higher frequency components, and so that 20 kilohertz signal often drops down to the range of 3 kilohertz, or at large distances it even drops down to about 1.5 kilohertz, very close to the upper range of the muzzle blast. And in those cases, such as the Oasis apartment, the two signals in terms of frequency response begin to look very similar. And these are all the things you have to understand and know and comprehend to identify one of these sounds as a gunshot sound. An AR-15, like what the LVMPD discharged inside of room 135, when it's recorded, is just all over the place because there's so many reflections that it's just all mixed and confused, and it's very hard to extract, shall we say, the real signal that's associated the muzzle blast and the supersonic crack, just because there's so many reflections. It can be done, but it's, every time you do a filter, it kind of, lessens the probability that you know precisely what the signal is. Let's just put it that way. You have different calibers of weapons being used that night, and those produce a slightly different sound. When you have the bullet traveling in a direction that's not towards you, that is away from you, then you lose the supersonic crack. And that's the situation where shots were fired down the hall, and those supersonic cracks, probably got trapped inside the room until the bullet made it through the door, and then supersonic cracks were created again out in the hallway, and then those hit the walls and just went everywhere, propagated up, down, sideways, through the vents, through the fire escapes, blah 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 blah. But anyway, with those down the hall shots, all that was left was whatever was inside the room, and that would be the muzzle blast, because even though the supersonic cracks are reflecting, they're high frequency, they get absorbed quickly, and they're mostly headed in the direction of where you're firing. So out of the window would come only the muzzle blast, and because it has a distance to travel, and it's being absorbed, and the most of the energy is being associated with reflections inside the room, you only get a very small portion of that signal coming out, and therefore it's radically attenuated, and you don't hear much of it. So all of these factors and things have to be taken into and accounted for when you're trying to decipher gunshot acoustics. Fortunately for us, most of the shots are very, very clear. All of the volleys and the first 6 shots are extremely clear in terms of having both a muzzle blast and a supersonic crack. That is, the bullet was headed outside in the general direction of where the recordings were. By general direction, I mean within 180 degrees. And actually within 90 degrees if divided by 2 and make it symmetrical about the origin. So, let's talk about measuring those things. When you heard that sound, just as when you're listening to a video from the Vegas phenomena, what inferences can you draw? Well, first you have to know what type of sound you're dealing with, because each of them has a different mode of propagation. As I've explained in numerous different videos, the muzzle blast propagates in a way which you would expect. The further away from where the source of the sound is, the lower it gets, and it travels evenly in most directions. And if you're in a line with the source, if your recording location and the source are in a planar line, that is, you're at the same elevation, then it's pretty easy for you to say, well, it's just the distance divided by the speed of sound. So let's start drawing some graphs. If I hear a sound, let's see what green looks like on this background. If I hear a sound and I'm here, okay, and this is kind of, if you pulled up Google Maps phenomena, we're looking at it from an elevated position as though it's a 2D representation of everything that's going on. So first we'll deal with the situation where everybody's on the same plane, i.e. at ground zero elevation. I hear a sound. If it's a muzzle blast, and the shooter was on the ground, and the shooter is somewhere, and that sound got to me it took that sound. Well, how can I write this? You hear the sound, and you know it's a muzzle blast based upon the frequency and the duration. That's the first thing. Then, if you have a clock, and you measure the time from when it was fired to you, then you can calculate, based upon that time difference times the speed of sound, a distance, which in our case, that night it was about 1,100 feet per second. So if we have a delta T of 0.5, then we just divide that by 2, and we get 550 feet would be where the source of the sound originated, which, would be a pretty big circle off the chart on the right hand side and whatnot. The difficulty comes in getting that delta T, because we don't know when the shots were fired. And with 1 point, we can't make pretty much anything. Oh, our ears pick it up and our head turns. And what's really happening is you have 2 recording locations, 1 in each ear. And with that information, the brain can basically do a shooter localization. So it turns your head in the direction of a muzzle blast towards where the shooter is. Now that's presuming that you hear a direct path muzzle wave. If you hear a reflection, you're going to point towards where the reflecting object is. So we do that, and then we somehow get the delta T. We multiply by the speed of sound, and we've got this estimate of where the shooter is. And if you want to incorporate where your head turned, then you might even be able to provide that second point, which this is a direction of what you've heard it, and conclude that the shooter was over here. But you'd have to be very, very careful in this, because how the sound got to you is not always clear. Do you have a clear line of sight? Well, how do you know if you don't know where the shooter is? Because the shooter could actually have been over here, and there could have been some object there, and the sound, that muzzle blast, could have come to you via reflection, and you don't know that ahead of time. So even though you might have a clear line of sight to something up here and conclude that's where it came from, you don't know, it could have come from over here. And that's the difficulty. So what we typically do is we have multiple observations. We take and we add another observer somewhere over here, and we measure the delta T. And in this case, let's say it turned out to be 0.3, and so 0.3 times the speed of sound gives us 330 feet. And then we draw another circle, and we start localizing down where the shooter is. All right. Let's just focus on the delta T portions of these. So, and how do we get these delta T's? Well, as I explained in one other video, you can take events that are common to both videos visually, and you can synchronize the videos based upon those events. For me, often I will use the sign out in front of the Mandalay Bay, called the marquee, and I will look for these transitions from dark to light, or a little boat going across, or some event which is very distinguishable in a limited number of frames. And then if I have a recording, let's say here and over here, well, let's call this point A and this one point B, then I can synchronize these two videos. And after I synchronize those two videos to that event, then I can measure the time between when that event occurred on the video and the time in the sound. And that will give, and so for example, if I have a gunshot sound, which will presume that you can identify it as a muzzle blast, because otherwise this whole analysis does not work and you could not know and apply the same physics. Let's say that here I heard it at 0.3 seconds after this visual event, and over here I heard it at 0.5. So now you see immediately that we have a way of comparing when the sound occurs on these videos, and we know that because this is a muzzle blast, that the first person to hear the sound must be closer to the source. So in this case, we would conclude that point B, because we heard it at point 3, is closer to the source than point A by 0.2 of a second. And so we could conclude that point A is further away by 0.2 by 1100, or 220 feet further away. We can't tell where the source is, only that we're further away. But we can tell who's closer. So, in that case, if we come along and we change the shooter's location to be somewhere else, these numbers change. And you can then say that the shooter is somewhere else. I'm not going to go into great detail here. What I really want to explain is that two things, and what we're talking about is how the shooter varies, and I'm going to go into that in another video, but that if the location of the shooter changes, these deltas change. Now, we've been talking about muzzle blasts. What does that mean? And we've been talking about being on the same ground level. When we're on the same ground level, let's take a non-ground level situation and talk about that for a moment. We can leave the sign there just for purposes. We're going to presume that it's synchronized. If we have, now I'm going to take and look at it from a side perspective, and I'm going to put the ground below us like that, and I'm going to put the shooter at an elevated position somewhere up in here. This is the source of the muzzle blast, and I'm going to put two observers, one here at X, one over here at A, and they're going to be located 100 feet apart. Okay? For those who have listened to my channel, you know that the time from the path from the muzzle blast to X and the path from the muzzle blast to A determine the time of arrival of the muzzle blast. That is, if this path is shorter than that path, then the muzzle blast will get to A sooner than X. And to determine how much, we simply take these distances, which let's call this X bar and A bar, divide them by the speed of sound, and you come up with the time it takes for each one. And then you could subtract those two and get overall delta, and that delta would tell you the difference in path length between these two. In other words, it would tell you this distance, how much further away. What it would not tell you is this distance. Okay, so you cannot say that the delta t between these two times of arrival is 100 over the speed of sound. It doesn't work that way. But that's what a lot of people try. They try and say, well, you know, this one arrived at 0.3, this one arrived at 0.5, therefore this distance is, if the speed of sound were 1,000, is 200. Does not work. They also try and say that because this one's closer, that the shooter must be somewhere in that direction. Doesn't work again. Okay, so you have a couple of major things here. First, you have to identify that it's a muzzle blast before you can say anything. And second, you have to make some real presumptions about whether or not it's at your elevation or an elevated position, and take enough measurements to eliminate that variable. In this case, it's going to take more than two. It's going to take at least 3 or 4, because we have a 3-dimensional space, and the elevation is an unknown variable. So you have to be really, really careful when you're making these conclusions based upon that. And there is a geometric relationship here. That is, you can let's redraw this. And once again, if we have the shooter up here, And we have point A here, point B there, and we have these paths between them. And this is A hat, this is B hat, just that's the distance of that. And then this would be a third distance. There is a geometric relationship there, but it's not simply B minus A. You have to first measure this angle and then apply some trigonometric function there. And I hope that makes sense, because if you look at this, then you could arc it up here like that, and you would find that that doesn't arc the same way as this one, and the error between those two is this, which is a function of how far they're out and the elevation. And I won't go into the math of calculating that, but I just want to bring it to your attention. There's an error in assuming that everybody's on the ground and that the distance between observers on the ground, and therefore the time between them and the time of arrival of the sound, even a muzzle blast, is not simply the distance between the recording locations divided by the speed of sound. It has to be the difference in path lengths between the source of the sound and the observers, which for an elevated position adds a extra unknown variable, and therefore you have to take more measurements to eliminate that variable. Now, for really long distances away from the sound source of the sound, that distance, this elevation, becomes fairly negligible, and you can make an approximation that it's the distance between these. But when the distance in elevation is approximately equal to the separation between A and B, then it plays a tremendous amount. And you'd be wrong in estimating the distance as simply the distance between A and B. Make sense so far? I hope so. Now that's for the muzzle blast. Let's talk about the supersonic crack. Let's say once again you heard that sound that I gave you initially, and let's put presume this is the venue of Google Maps, and you put somebody over here on the boulevard, and you put somebody over here on Giles, and you heard a sound. Okay, you don't know what that sound is, and let's say the distance between the two is 1,000 feet. Now let's make it 1,100. That way it's more accurate for that evening. Let's say it's 1,100 feet between the two. Then if the speed of sound that night was 1,100 feet per second, you would expect that if the sound originated here, it went over there, and at 1 second later. Well, there's several mistakes with that. First off, the source of the sound did not originate here, probably, and it probably did not originate in a line between those two, along the same line as those. Now, if by chance you have lined up that, it might be better. And if it's not elevated, it might be better. Okay, but generally speaking, that won't be true. And that was muzzle blast. If it's the supersonic crack, then you've got a whole different set of physics involved. And these 2 points, depending upon how that supersonic cone comes, could actually hear the supersonic crack at the same time, simply because they lie upon a situation which is parallel to the leading edge of the supersonic cone. That is, if the supersonic cone, if the bullet is coming kind of, oops, I wished I had the other color going, there we go. If the bullet was coming like that, and the supersonic cone was shaped like this, okay, which is entirely possible, then you'll notice that the supersonic cone is essentially parallel to the line between the two people, and that therefore the distance is the same, and they both would hear the supersonic crack at the same time. So under the right conditions, the time between them for a supersonic crack, it would be 0, the delta t between them, because they hear it at the same time. Now that's rarely the case, obviously, and It depends upon your locations, but if you are, let's say, if we draw the venue more accurately, first off, we know that, well, I know that the bullets were being fired like this. Okay? And so if we put somebody down here, let's say at the fountain, and we put somebody over here near the cop cars, and then we put somebody up here at the medical tent, all those people are likely to hear the supersonic crack. Well, first off, it forms a line on two-dimensional space, not three-dimensional. So that crack, which if you look at it from a side view, is shaped something like that, and it's pointing down because the bullets are coming down, and therefore it's kind of like this. And so that cone is kind of parallel to this line if you know in the right perspective. However, the elevation is different. The elevation at the fountain between the bullet and this is probably 200 plus feet. At the cop cars, it's probably, depending on where the bullet hits, of course. Let's presume it hits out in the dirt on the towards the church. Here it's probably more than 100 feet. Here it's probably more than 35 feet. And so correspondingly, because the cone is parallel to the earth, let's presume, then the propagation distance is somewhere on the order of these things. And so the crack then would be the inverse of these numbers. Now, how can I put this carefully? The 135 feet away would hear the crack close to the bullet trajectory. The 200-foot one here would hear the path close to the window, and the muzzle blast and the crack would approximately arrive at the same time, and this one would be somewhere in between. As the downrange distance increased, the lag would increase. As the distance between the observer and the bullet path, which is above them, increases, which it does in this way, the lag increases. So these would not hear it at the same time. And I can't give you an exact estimate of what those are because I'd have to run it through the formulas. And let's see if we can come up with a better example here. Well, let's do this. Back to our original example where we said that it was possible for them to hear it at the same time. If let's draw that previous example that I was talking about. Let's look at it. Here's the ground. Here's Mandalay Bay going up. Here's the fountains. Here's the cops on the corner. Here's the first aid way out there. And the path of the bullet, let's presume, is going something like this. So it's overhead to everybody. But let's further assume that they're all in that line that I showed you earlier. Then here the muzzle waves would of course arrive along these paths. Okay. And the supersonic crack would arrive. In the case of the one that's close to the Mandalay, it'd probably be originated there and come down there. So those two paths are from between the muzzle and the supersonic crack are about the same. This one would travel a little bit further out, and the supersonic crack would be origined there and come down there. And for this one, it would be origined maybe right about there and come down there. So, to determine when you hear it, this case, which is the near case, it is simply the elevation, roughly, plus this little distance divided by the speed of sound, which if that's 300 foot in the air, then we're going to get about a 0.3 second time of arrival for the supersonic crack. Here we've probably lost, 20 feet, 30 feet or something. But the bullets had to travel this distance. So it's probably going to be, let's see. It's probably going to arrive at, I would guess 310. And then this one out here at 1,000 feet, we have to take the time it takes the bullet to travel that 1,000, not quite 1,000 feet, let's call it 900 at Mach 3, so that would be 0.3 seconds, plus the time it takes to go that 50 feet, which would be 0.05 seconds, so we're probably going to hit a grand total of 0.35 is when the shockwave would arrive. So anyway, we could have a situation here where, you see, these numbers aren't too far apart, but they are increasing, and because they're all in a line, it's kind of a linear predictive model based upon the angle between the bullet and the ground, which we'll call theta. Okay, but back to something more simple. What I really wanted to point out here was, and I think I took a long ways around it, that if you assume that the sound you heard was a muzzle blast and it actually turned out to be a supersonic crack, namely a shock wave generated by a supersonic projectile, then all your calculations are thrown out the window if you're using the physics for a muzzle blast or just a normal sound. And that will happen every time you hear one of those 308 shots. The 6 shots that occur between volleys 4 and 5 and the 2 that occur after volley 12 are dominated by the shock wave. And correspondingly, there are a lot of sounds for a lot of volleys coming from the other rounds where the supersonic crack is louder than the muzzle. So you have to be careful. You have to properly identify which sound you're dealing with before you can make any assertion about the nature of how fast the sounds should arrive at your location. And I think that's the takeaway from this little blurb of a video. You have to know which sounds you're dealing with. And if we go back to my little sonic visualizer session, and I expand these out, then it becomes very, very clear. There's no guessing here at all about which ones are the supersonic cracks and which ones are muzzle sounds. These things on the bottom frequency register here are the muzzle blasts, and these things up there are the supersonic cracks. Now you'll notice in this situation that the supersonic cracks are kind of blurry. You can still tell where they start, but they're blurry, versus the muzzle sounds, which are not blurry. They're fairly clean. And that occurs because of the frequency of them. That is, the supersonic crack is much higher frequency, and hence when it has to reach you, it has to travel a line of sight, and when it doesn't, you get a lot of reflections, and that's what's happening here. Whereas the muzzle blast, being a lower frequency, can just kind of fade right through that lattice that these people are hiding behind without any worries directly from the source. And that there's a little bit, of course, of reflections, but you still get the primary wave, or that's not true in the supersonic crack. In this case, so you see that the reflections almost dominate the primary signal. Whereas let's see, I do have another one up here. In this case, what you see is that the Once again, you can easily distinguish which is which. These are the supersonic cracks, and these are the muzzles, and they're extremely close together. But you'll notice that the muzzles are wider than the supersonic cracks, and the muzzles are lower frequency. And I don't know what that is at the moment. So, in this case, the supersonic crack being clean, this is a primary direct path signal received, probably from a line of sight situation. Similarly with the muzzle blast, a line of sight situation. So this videotape, without even knowing where it's at, I can tell you straight up that they have a line of sight to wherever the shooter is from, and that they are at quite a distance and quite an angle from him. Now, angle isn't what you think it is. Angle has to be measured in a three-dimensional thing, because if the bullet is high above you, then the angle also increases, and if the bullet is either north, south, east, or west of you relative to its path, then that also increases the angle. But that's just some of the stuff you have to know before you can start playing and estimating where these bullets are coming from, what their time of arrival is, and even what type they are. But these are clear. And everyone who's doing this type of stuff and making these predictions needs to have a tool like Sonic Visualizer, where they can tell precisely which type of signal you're working with and where they start and where they end. Otherwise, you're just using your ears, and your ears can easily be deceived, because let's pull up Oasis. Oasis is far away. And this is the Oasis apartments we're talking about. And God knows what kind of condition I left this session in, because I tend to modify it a lot. So I'm pulling up the Sonic Visualizer session for Oasis apartments. Oasis apartments are a long ways away from the shooter. And because of that, the high frequency supersonic crack that we hear is generated almost at the same time as the muzzle blast. The path is very close in length, and therefore they occur close together. But the important thing is that the frequency of the shock wave, the supersonic crack, is reduced because it's partially absorbed during its travel to the Oasis apartments. So, and here it is up here at the top. Let's see if we can't make this a little cleaner. There we go. And eliminate all the crud. And here we see that there's this regular cadence of signals, and that if we drop the frequency measuring tool, or this one, then we'll see that the top end of these signals are 2600 hertz. The top end of the other ones probably about 939. The center frequency, or most dominant and intense, is about 407 hertz. And these things are the muzzle blasts, the lower ones, and the top ones are the supersonic cracks, and their center frequency is about 1700 hertz. Whereas when you're at the bus stop or somewhere closer, these things go all the way up to 17 or 20 kilohertz. So this is an example of where these two sounds are starting to be very similar in nature, but they're still distinct enough that we can make out which is which. Because rarely do you find a supersonic crack having a low frequency component that's really, really strong. You have to be, on top of the bullet path for that to occur. And so this is the type of analysis. And if you didn't have a tool like Sonic Visualizer, and you could do this in Audacity because it does have spectrograms, and there's a number of other programs out there. And if you're good, and for Oasis apartments, you can actually see it in the waveform. If we look here at the waveform, you can make out which is which signal. See, the very narrow ones are the supersonic cracks, and the wider ones are the muzzle blast. But it is hard. It's much easier to do it with a frequency view than it is with an amplitude view. And if you were just listening to this, you would say, without the benefit of this analysis, you would say that the gunshot sounds start there, and your timing would be off accordingly because the first muzzle blast starts there, and that's the most accurate sound. The cracks, these supersonic cracks, they vary in when they begin based upon the trajectory of the bullet. The muzzle blasts do not. They're independent of the trajectory of the bullet, and that's why they are the basis for calculating time of arrival and when the bullets were actually fired. Okay, kind of getting off into the weeds here, but this is an emphasis on you have to know what type of sound you're dealing with before you can make any projections as to where the shooter is, what its path is, blah 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 blah. And I hope that I've hammered that in now. All right, let's move on to the next subject.